All right, on to our second topic. You may recall from the lecture from Pedro that there is a class of learners called analogizers. It's one of the 5 tribes of machine learning. And analogizers make their inference by comparing something with something else. And that something else will help label what this something is. So for example, if I have a test instance, I'd like to compare it with the training data and find something similar in the training data that's similar to my test data. Whatever that training data is, I'm going to transfer in some way the label for that training data over to our test data. So to classify a test instance, we assign it to its closest neighbor. That's what we mean by a nearest neighbor algorithm. And this is actually pretty easy to implement. By training, we just mean to memorize all of the training data so it can become handy when we need to use it for testing. In testing, what we want to do is compute which of the training instances is the closest one to the test instance. One illustrative way to think about nearest neighbors is to think about how we would use it for images. Here, there's always a problem that we've illustrated even in the first week. We see a semantic gap where we, as people, can understand that this image is a cat. But the computer doesn't see that. All it sees is a very large grid of numbers. And in fact, we have quite a lot of numbers here. If we have an 800 by 600 pixel image, and we have 3 channels of color, RGB, and let's say we're not representing each of those levels with a lot of fidelity, just 256 different levels of intensity, then we already have 1,444,000 numbers or integers to encode. So to understand nearest neighbors, let's apply it to the CFAR10 dataset. This is a dataset of tiny images that represent 10 different classes. So for example, we have planes here, which is this entire column, different illustrations of planes, and cats, right? Cats, as you can see, are quite varied in pose and color. The dataset comes with 50,000 training instances and 10,000 test instances. Now, the key to nearest neighbor is really deciding what counts as near. What do we mean by this? Well, we can use different types of distance metrics to decide which things are near or far. One that we can use is the L1 distance metric. This one says for a particular test image, we can compare it against any particular image in our training data set. Let's say the first image in our training set. And what we're going to do is we're going to do a pixel-wise difference between the value, let's say the red value, of the pixel in the test image compared with the training image for that particular training image, like the first one. And we're going to sum up these pixel by pixel differences over the entire grid of pixels. So this one, 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 all the way until this one here. I'm going to sum up all of those values, and then that will be whatever the distance metric for L1 will be. So here you can see this at work, right? Let's say we have this test image, which has a value of 56 in the red channel. And the first training image has, in this upper left-hand corner, a value of 10 for the red channel. Then the pixel-wise absolute difference for that pixel by itself is 46. And when we aggregated over all of these values here, summing them all up, then we're going to get a total of 456 for this 4x4 matrix. So obviously, the smaller the difference is, the nearer that image is to this particular training image. So what does nearest neighbors actually look like? Well, let's take a case of a free class problem, let's say distinguishing between cows, chickens, and dogs, and plot them just using two input features, whatever those input features are. So it could be their difference in L1 distance plus some other metric. So we could put L1 on the bottom here and another metric, another distance metric here. It doesn't matter. It just means that we're thinking of L1 as our first feature and distance metric 2 as our second feature. In this case, what we can see is that nearest neighbors help us define a neighborhood of points that are going to be associated with a particular label. So if I have a new point over here, it's going to be classified as red, or whatever red stands for. And over here, if I have another image that came in that happens to be here, then it's going to be a green image, maybe a chicken. Let's take a look at this a little bit more closely. What we can see here is that the individual points actually define a polygon. This is a Voronoi polygon, basically that each point defines a polygon where the boundaries of the polygon are equidistant from the next point. So for example, let's focus on this point here, number 9. You can see that the boundaries that it's drawn are equidistant from the points. So between 10 and 9, there's this line that we can draw, and the boundary between them is equidistant on both sides and perpendicular, right? The same for 8. And here, point 4 defines a large part of the boundary. Point 7, a small part. Point 3, a slightly larger part. And point 5, the last part. So any point lying within this polygon will then be associated with whatever label point 9 is. And in the diagram on the right, you can see that several points that might belong to the same classification. Let's pretend here 9, 3, 7, and 4 all belong to the same class. Then we would have a block of area where any point that fell in this shaded region would belong to the same class as what those belong to. Here's sample output from nearest neighbors on the CFAR10 dataset. You can see some interesting examples here of things that it gets right and wrong. So for example, in the right column, you can see that quite a lot of the boats here or ships are actually classified correctly. In fact, all of them except for the very last one seems to be correct. But there are certain cases in which even the nearest neighbor, the first nearest neighbor, which is represented by the first column, is wrong. So for example, here you can see this is a dump truck, but it gets it wrong. It thinks the first image is the most closely related one, which is a horse. So it would actually take this truck here and classify it as a horse. Similarly, for this airplane, this is a US stealth fighter, it would be categorized as some type of, I don't know, insect or spider instead. So that would be wrong as well. In summary, we've introduced the nearest neighbor algorithm. It's a very interesting algorithm because it's parameter free. It doesn't have any parameters to tune in this case because it doesn't encode the model that way. It needs to remember all of the data points when it uses it for classification. So we consider this a non-parametric algorithm. It requires immense of time to apply because it has to cycle through all of the test data points to see which point is closest. In fact, this is something that we can speed up. And it also has this crippling point where it doesn't work in high dimensions. And I'd like you to think about why that is. We'll discuss this more in the post lecture.